Welcome to Module 12 of an Introduction to Engineering Vibrations. Today's learning outcome is to now solve the differential equation of motion for the simple single degree of freedom system that we've come up with. And I want you to buckle up your seatbelts today because we're going to be brushing up on some math that you may have not seen for a while, so you may have to go back and review some of your basic math. Again, we're focusing on taking the physical model that I came up with for the actual system and putting it into a mathematical model, which ends up being a differential equation of motion. So here's where we left off after last module. We had the bungee system or the amusement park ride. We gave it some initial conditions so it's vibrating. We came up with a differential equation of motion that describes how the system's moving. mq double dot plus kq equals 0. And to solve the DOM, I'm going to use the method of undetermined coefficients. Hopefully you've had a course in differential equations of motion. If not, you should take a course in that to have the background necessary to continue on this in this video. But we're going to assume a solution. Since the differential equation involves the function q and its second derivative, and we've got to add it together, those terms together, and have it come up to 0. That means q double dot and q must be of the same form. So I'm going to assume a solution where q and q double dot have the same form. And you might want to stop the video and think about for a second what kind of a function would be able to do that. And after you've thought about it, q, if we made q a function, a exponential function, we would always come back with an exponential function when we take the derivatives, first derivative, second derivative. And so we can substitute that in the DOM and force equality to the right-hand side being equal to 0. So here I have my first term, q double dot will bring down the lambda twice. So we have lambda squared times e to the lambda t times the ma, right, plus k times q, where q is the assumed a lambda t. To have that equal to 0, we can factor out the e lambda t, and we end up as shown. Now, if a, we could say a e to the lambda t is equal to 0, but that would then say that there's no motion. The system is just sitting there in static equilibrium, and that's not very interesting. So we call that the trivial solution, because q equals 0, because q is a equals lambda t. So the much more interesting solution, and the one for the vibration we want to analyze, is the characteristic equation where we set m lambda squared plus k equal to 0. And now we can solve for these characteristic values, or the lambdas. So lambda ends up being minus k over m, and so that can be lambda squared equals minus k over m. So there's the solution for lambda. If I have plus I squared times square root of k over m, a plus I times a plus I is a negative. Negative times square root of k over m gives us, satisfies the equation. Now if I square minus I square root of k over m, I've got minus a minus is a plus, I times I is a minus, times square root of k over m. So again, that comes out to minus square root of k over m and solves the characteristic equation. So those are my lambdas. Now I can substitute those back into the assumed solution. Qt equals a e to the lambda t. And there is my general solution. I've got my undetermined coefficients, a1 e to the I square root of k over mt plus a2 e to the I minus I square root of k over mt. There it is again. Generally, we want to, it's not so easy to work with complex exponentials unless you've done it for a while. So we like to look at sines and cosines. And to change the exponentials into sines or cosines, we're going to use a very well-known identity, or Euler's formula, which says that e to the I theta, some argument theta, is equal to cosine theta plus I sine theta, where in this case theta would be the square root of k over m times t. So we're going to be able to come up with some sort of a general solution, which is going to be a combination of cosines and sines times, again, undetermined coefficients. But these undetermined coefficients, B1 and B2, are going to be different than the A1 and A2. And we'll see what those are. So here we are. There's my complex exponential form. I'm using Euler's formula. I'm going to substitute Euler's formula in. And so I've got e to the I theta, where theta equals the square root of k over mt, is equal to cosine square root of k over mt, plus now I sine square root of k over mt. Now I've also, for the second term on the top equation, I've got e to the minus I square root of k over mt, and that's shown there. With those two, I substitute them into the top equation. So I have A1 times the quantity shown plus A2 times the quantity shown. And then I can collect terms. And I've got Q equals A1 plus A2 cosine square root of k over mt plus I times A1 minus A2 sine square root of k over mt. Now I know I'm going fast, but the good news is with these modules is that you can go back, stop the modules, go through step by step in the math, make sure you understand it, or go to YouTube or Khan Academy and look how you solve differential equations, and you should be able to follow along. We know that the actual displacement Q is real, so the imaginary value I must vanish. We can't have the imaginary value. So to do that, A1 and A2 must be complex conjugates. And so here I've let A1 equals 1/2 B1 minus IB2, and A2 be the complex conjugate, which is 1/2 B1 plus IB2. So you can see on this top term here, A1 plus A2 will get rid of the I's and just end up being B1, and A1 minus A2 will get rid of the B1s and end up with minus I squared B2, which multiplied by I will get rid of that imaginary part. And so I end up with our general solution there. I now can put in B1 and B2, and it becomes a real value for Q, B1 cosine omega, or cosine theta, which is the square root of k over mt, plus B2 sine square root of k over mt, after substituting in A1 and A2. Okay, that's the solution. Now we can go ahead and analyze it further, and we'll do that as we continue on in our modules. So today's summary was just to solve that differential equation of motion for the simple single degree of freedom system. See you next time.